Hello again. In this video we're going to start looking at smart pointers. First, let's quickly remind ourselves about traditional pointers, which are definitely not smart. The traditional pointer is inherited from C, it's a built-in type, and variables which are pointers store numbers which represent an address in memory. This memory could belong to a variable on the stack, for example if we're passing a function argument by address. Or it could represent memory which has been allocated on the heap with new, in which case we have to manage the memory and remember to release it by calling delete. Typically this is when you have a variable length array, and in C and older versions of C++, this was the only way to create an array if you didn't know the length at compile time, or if the array was too big for the stack. And we can also use traditional pointers for polymorphism. We can have a pointer to a base class which actually points to an object of a derived class, and when we call virtual functions through this pointer we get the version from the derived class. There are many drawbacks to traditional pointers. They're a common source of bugs. The main problem is there's no concept of ownership. Nobody actually owns a pointer. Any code can reassign a pointer, overwrite it, release the memory, or set it to null. And also there's no clear indication of whether a pointer is still in use, so you can end up releasing memory twice, which will cause a memory error or probably a crash, or not releasing at all, in which case you get a memory leak. Fortunately, C++11 now means that you don't need to use traditional pointers very often. If you're working with stack memory, we can pass by reference instead of passing by address. If we want a variable sized array, we can use the library vector class. If we're working with heap memory, we can use these smart pointers. And if we want dynamic binding, we can use smart pointers again, or we could use references. So what are smart pointers? Smart pointers are classes which encapsulate allocated memory. The class has a private data member which is a pointer to this allocated memory. The smart pointer object has ownership of the pointer and the allocated memory, so nothing from outside the class can interfere with it. The only way to access this memory is through public member functions of the class, and things like pointer arithmetic are not allowed. Smart pointers are implemented using the RAII idiom. The memory is allocated in the constructor and released in the destructor. So this guarantees that the memory is always released, either at the end of a scope or if an exception is thrown. Smart pointers will save you a lot of work, both when coding because you don't need to keep track of all this memory and who's using it, and also when debugging because you won't have so many crashes to debug. So let's look at the smart pointers which C++ offers. The first attempt was AutoPointer in C++98. So this had the basic idea of encapsulating the memory inside a class. Unfortunately, it has some rather weird semantics. If you copied an AutoPointer, the copied from object had its pointer set to null, so in effect the memory was transferred to the object you were copying into. And this caused a lot of problems because as programmers we tend to assume that if we copy from something it's not going to be modified, and there's a lot of code which assumed that copied from objects are still valid. For example, if you store auto pointers in containers or use them in generic code, then you could get unpredictable behavior. So this was a bit of a flop really, and it's now been removed from the language. C++11 has a unique pointer which is a fixed version of AutoPointer if you like. It does everything that AutoPointer should have done. The reason why it couldn't be done earlier is because move semantics only came in C++11. So with a unique pointer it cannot be copied or assigned to, but the memory can be transferred from one unique pointer object to another one. So this solves the problem with AutoPointer. If we want the memory to be transferred from one object to another, we need to do that explicitly by invoking the move constructor. So we need to put the copied from object inside a call to move, and then when you look through the code it'll be very obvious that this object has been moved from and is no longer valid. It's not possible to accidentally transfer the memory like it was with AutoPointer. If you try to copy a unique pointer then the code will not compile. There's one other main smart pointer in C11, which is the shared pointer, and as the name suggests, this can share the allocated memory with other shared pointer objects, but it is still encapsulated inside the class and can only be accessed via member functions. The sharing is managed by something called reference counting. If you're not sure about that, then I have a video on that later on. This means that the memory is only released when there are no more objects which are sharing it, so the last object which is destroyed will release the memory. So this is quite similar to a garbage collected object in other languages. The shared pointer has more overhead than a unique pointer. It takes longer to do operations, so you should only use this if you need the extra features. Okay, so that's it for this video. I'll see you next time, but until then, keep coding.